So what I'll do is, I'll give you real Tom and Jerry utility functions, and you can try that. Okay. So this is not really, I wouldn't call that Tom and Jerry, because they are not really. I mean, I agree that eventually it's about that fight, but if you really think about it, Tom's satisfaction level is improving in if Jerry consumes more of cheese. I mean, that's lexicographic preference, are monotonic, right? So let me give you real Tom and Jerry, and then you can do this as an exercise yourself. Okay, so Tom's utility is CT minus CJ. So the higher the CJ is, the lower the utility of Tom. Okay, and you can say Jerry also has a similar kind of preference. Let's say CJ minus CT. Okay, so this is, you see the fight here. Okay, can you just tell me what will be the set of efficient allocations in this case? 2.5. Okay, 2.5 is one Pareto efficient allocation. Are there others? Absolutely, all the feasible allocations are Pareto efficient. Okay, it's actually kind of straightforward. So if you just rewrite this adjusted utility function, okay, the adjusted utility function of Tom will be CT minus 5 minus CT, right? Which is actually 2 CT minus 5. So if it is 2 CT minus 5, it's just increasing in Tom's consumption. Utility is increasing in Tom's consumption, and similarly Jerry's utility is also increasing in Jerry's consumption. So I mean, every allocation will be Pareto efficient, because no matter which allocation you consider, okay, if you move to the right, you will make Tom better off, but you will end up making Jerry worse off. And if you move to the left, you end up making Tom worse off, and Jerry will be better off. So the key thing here is this, that no matter where you pick a point, any movement away from that point will necessarily make one of them worse off. So what that means is, that particular allocation is Pareto efficient.